Okay, so if I remember right, I think the last thing we talked about yesterday was this idea that in the same way that you can differentiate position to find instantaneous velocity, you can differentiate angular position to get instantaneous angular velocity. All right, I did not write up an example of that because I figured it's the exact same thing we've been doing. You just didn't differentiate with respect to t. Would you guys like to see an example where you take the derivative, or are we all good with how to do that? It's literally the exact same thing, except it's going to be theta of t instead of x of t. Cool? Okay, that was what I had assumed. Okay. And then again, just a quick reminder, I want to make sure, I think we did this yesterday, but I want to make sure that everybody's good with it. These jumpers, remember, all of them are the same format. It's always linear quantity equals angular quantity times radius, right? And what was the condition? What do you have to ensure that you do to use that equation? Yep, your angular quantity has to be in radians. Okay? Cool. All right, so now, obviously, and I think this was sort of where we stopped yesterday, obviously how quickly something is spinning can change, right? In the same way that how fast something is going linearly can change, right? So we can talk about linear acceleration, right? So this is, the definition of acceleration. It's how much your linear velocity changes per unit time, okay? And similarly, we can find our angular acceleration the same way by finding the change in angular velocity per unit time. All right? I'm realizing I recycled these notes, and I probably should have been a little more specific. I wrote it up here, but didn't here. Technically, this is the equation for average acceleration, right? And similarly down here, this is average angular acceleration. For the exact same reason, right? Because the rate at which you're accelerating at might be changing. Cool? All right, any problems with this? Everybody good? All right. And then for the exact same reason, you get the same style jumper equation. So the linear acceleration equals the angular acceleration times the radius with the same condition that your angular acceleration must be measured in, what units are we going to measure it in?
Radians per second.
Yeah, radians per second or radians per second squared. Okay. Good. Alrighty. So, now, in the same way that you can differentiate position to get velocity, you can differentiate velocity to get acceleration. And again, you've got the same angular correspondence, right? So the derivative of linear velocity gives you linear acceleration, instantaneous. And the derivative of angular velocity gives you instantaneous angular acceleration. Okay, so same relationships that we dealt with last time. The biggest difference here, you guys, is units. We're no longer talking about meters per second or meters per second squared. We're now talking about radians per second or radians per second squared. Cool? All right. Okay, cool. So there's that jumper equation again. I did some cutting and pasting, so a couple of these equations show up more than once. All right, so all of those constant acceleration equations that we learned first semester, or really that you learned last year, right? Displacement is 1/2 at squared plus vit. All these guys, they have an angular correspondent, right? Is that the right word? Angular, whatever, you know what I mean. But they're all the exact same equation, right? Change in x becomes change in theta. A becomes alpha. Vi becomes omega I. All right? So in a lot of ways, I don't memorize these. Because I know that they're the exact same as these, and you just replace linear values with angular values. Okay? Now, one of the things I've been saying to you guys is that I feel like there are some of you guys who don't know these equations as well as you should. So this chapter will give you a lot more exposure to those because you have to know these equations to do this chapter. All right? The one other thing I'll comment on. Where is it? You know what? Here. So remember, you can only use these equations if the acceleration is constant. Okay? All right, there was one problem on the midterm where, I don't remember the exact value, but it was something like the acceleration was 4t or something. And looking at work, a lot of people tried to take this acceleration and plug it into one of these equations. Okay? But the fact that the acceleration is 4t is telling you that as time changes, so does your acceleration. Right? So this is not a constant acceleration. Cool? So how do we deal with these types of things, you guys? You got to integrate, right? Okay, taking an integrator. All right, so just make sure you're aware of that. These equations here only work if your acceleration, or now angular acceleration, is constant. Cool? All right. Let's do an example here. Radians. I don't know the answer to that. I'm not sure. But yeah, SI, you'd have to use radians. For any of these equations to work. Well, I shouldn't say that. Actually, I'm glad you asked that question. A real quick comment about these, you guys. So with these equations, is there anything magic about meters? No, you can use feet or inches or whatever, right? Same thing over here. You can use any of these equations. You can use degrees if you want, or rotations. All right, the only time that it matters is when you use one of those jumper equations. Cool? All right. Okay. All right, so here we go. We got a carousel at a fair. It's got a radius of 3.5 meters. It says it accelerates from rest and takes 4.5 seconds to reach a maximum frequency of 0.5 hertz. So we're trying to find the acceleration. So again, a lot of this chapter, you guys, just boils down to units. So I gave you this frequency. Well, here, so let's write down what we know. Let's see, we know the radius is 3.5 meters. We know that it accelerates from rest. And at the end of 4.5 seconds, it hits a frequency of, what is it, 0.05 hertz. So how is frequency connected to this chapter, you guys? Sort of. What is a hertz in this context? What do I mean when I say 0.5 hertz? Rotations per second, right? So this is 0.05 rotations per second, right? What is that?
Oh, it does speed.
Sort of. What kind of speed? Angular. That's your angular velocity, right? Just in stupid units, right? Because it's rotations instead of radians, right? So really, if I wanted to, I could find angular acceleration in rotations per second squared, in the same way that you can find acceleration in feet per second squared, right? But the answer's in radians, so I'm going to convert everything over. Follow? So, here we go. I didn't give you very much room to work here, did I? Sorry. So, let's see. So I'm going to go 1 rotation is the same as 2 pi radians. So this gives you 0.314 or 0.314? 314. Radians per second. All right, now, so I'm going to call this omega, but we ought to be a little bit more specific. Is the angular velocity of the ride always? That's at the end, right? That's the final. Right? Because it's going to reach a maximum frequency, right? Implying that it's speeding up until it gets to this final value. What's the starting angular velocity, guys? 0, because it says it accelerates from rest. Follow? Sorry, I didn't give you guys enough room to work here. I apologize for that. All right, so let's see if I can squeeze this in. So then now we can find our alpha just by using the definition, right? Omega f minus omega I over t. So we're going to get 0.314 radians per second minus 0 all over 4.5 seconds. Gives you that answer. Radians per second. Board work's a little cluttered there. Everybody good? All right. Now, it says through what angle will it turn in the time it takes to achieve its highest speed? So what am I looking for part B, you guys?
Change of theta.
Change in theta. Angular displacement, right? So I got to pick an equation. So let's see. I know my initial angular velocity, my final angular velocity, the time, and the angular acceleration. So really, you can use any of those equations. You know enough information to use any of these three equations. Or four, I guess there's four equations there, right? But yeah, the one that I tend to use, when you know the initial and final value, I tend to use this guy. Find your average angular velocity, and then multiply it by time. What's wrong, Alex? You're making this
Isn't there
spreadsheet.
another one? Isn't there the VF equals AT plus V? The one right above it.
Oh, that is, I gotcha, I know what you're talking about. You're talking about this. VF equals AT plus VO, is that what you're talking about? Yeah, that's the same as A equals VF minus VI over T,
Oh,
algebraified. Cool, but you're good to know that because this equation comes up all the time.
yeah.
And we also have the angular counterpart for it, omega F equals alpha T plus omega O. Cool? So yeah, that's for sure. All right, so anyway, so pick an equation. So I'm going to use, this guy, 1/2 omega F plus omega I times T. I hope you guys understand that when you use this equation, that this just represents the average angular velocity, right? Good. Now we can only use this if the acceleration is constant, which we are assuming here. I guess it doesn't explicitly say it, so I probably should have written that a little bit more clearly. Okay, so here we go. 1/2 our omega F is 0.314 radians per second. Initial angular velocity was 0. The time is 4.5 seconds. And you get 0.707 radians. Okay. Please make sure you're familiar with the other options for solving that, though. Okay. You really need to make sure you know those constant acceleration equations. All right. Any problems so far? All right. Question C. What's the tangential velocity? I feel like I haven't stressed that this much. So this chapter in particular, there are going to be tangential quantities and what are called radial quantities. In the past, we called them centripetal. Okay? So the idea is, as the rider is going around the ride, that was a weird sentence, he's going to have two types of acceleration, right? Because he's speeding up his linear velocity, right? So he's going to have a tangential acceleration, right? But also, because he's traveling in a circle, there's also what we previously had called centripetal acceleration, right? There's an acceleration directed towards the center of the circle. And for some reason, this chapter of the book arbitrarily begins calling that radial acceleration, indicating that it's directed along the radius. Okay? So if you see that term in the book, radial acceleration, that's what it's talking about. It's basically the same as what we were calling centripetal acceleration before. Okay? And this guy will usually be called tangential acceleration. I'm trying to think if there would be any other names for it. I don't think so. I'm sorry? No, so actually your instantaneous linear acceleration, in this situation, how do we find it, you guys? The idea is you've got acceleration in two directions. You've got acceleration horizontally and acceleration vertically. So yeah, you'd have to find your hypotenuse. You'd have to find the resultant vector. Does that make sense?
Yeah, so tangential velocity is not the same as
Well, so these are both instantaneous values. So at this instant, there would be some tangential acceleration.
So when you take the derivative of like position, it's instantaneous tangential velocity.
I see what you're saying. So to do this that way by using derivatives, you'd have to have an expression for vertical and horizontal velocity. You know what I mean? Because it's two-dimensional motion. So you'd be differentiating a horizontal velocity and differentiating a vertical velocity, and it would give you this exact same result. This would be your horizontal, this would be your vertical. Follow?
Yeah.
All right. Everybody good? Okay, so long story short, here we're talking, oh, wait, how did I get into acceleration? I was talking about velocity. Sorry. All right, so anyway, tangential velocity, we're looking for the linear velocity at which the rider is moving. So thoughts about how to do part C? We're trying to find, it says what tangential velocity will a rider at the outside edge of the ride reach? So in other words, yeah, so your rider's on the outside edge of the ride. So you can find the period. There's a way easier way to do it then. Yeah, we're trying to find the final velocity, right? At the outside edge. So, yeah, we just use a jumper equation, right? Look, we know velocity is angular velocity times radius. So that means that final velocity is final angular velocity times radius. In other words, our passenger reached a final angular velocity of 0.314 radians each second. And the problem tells you that the ride has a radius of 3.5 meters. So that's sort of your conversion factor of medians per radian, or meters per radian. Medians per reader. So multiply that out, it gives you pretty close to 1.1 meters a second. You had a hand up a second ago, Nate. Was that what you were going to say? Okay, somebody else beat you to it by a second. All right, are we good, you guys? So those jumper equations are really, really valuable because they allow you to convert between angular quantities and linear quantities. Cool? Worth reminding you of, you guys, is that, remember, for velocity, your velocity vector always points in a direction tangent to the path that you're following, right? Hence the term tangential velocity. Cool? Alrighty. Yeah.
That jumper equation with acceleration, does that give you tangential acceleration?
Yes. Yes.
That doesn't take out the radial.
Correct. Correct. Yeah, and I'm now trying to remember. I know radial acceleration comes in here somewhere. I'm not sure if it comes in here, but here, let me see what I got on the next chunk of the notes. Let's see. No, we just got two more things. All right, let's do this. I'm not positive if it comes up in this assignment or the next assignment, but I honestly don't remember putting it in the notes. So this is probably as good a place to talk about it as anywhere, because it comes up. So let's do this. What am I doing? So question B. Sorry, the tack went on. All right. So let's find the rider's acceleration. Now notice if it doesn't specify angular, it means linear. So to do this, this is exactly what we were just talking about. So we need both the tangential acceleration and radial acceleration. So this is exactly what we were just talking about a second ago. All right, so let's make that drawing again because I think it'll help you kind of visualize what's going on. So the idea is the ride is spinning around, but it's speeding up, right? Going faster and faster and faster. And now I just made my drawing really ugly, so I'm going to make a nicer circle. All right, so here we go. They're spinning around and around, going faster and faster. So there's one type of acceleration, tangential. So that's just going to be alpha r. Good. And I'm glad that you asked that question, Alex, because that's a distinction that I had not sort of painted out in the notes. So make sure you understand that jumper equation gives you the tangential acceleration. Okay? Now, the radial acceleration, we know that, right? What's the equation for centripetal acceleration, you guys? It's v squared over r, right? Right, and I guess this is as good a time as any to do this. Since we're talking about angular quantities, let's see if we can write an equation for this in terms of angular quantities instead of linear. Okay? So, well look, v is, how do I rewrite v as an angular quantity? Yeah, this is omega r squared over r, right? So you get omega squared r squared over r. So you just get omega squared r, right? So when you're finding centripetal acceleration now, radial acceleration, you've got two choices. You can either use v squared over r, or you can use radial acceleration is omega squared times r. Cool. What's the condition on your omega? Radians per second. Cool. All right, so any questions before we jump in and do the calculations? All right, so let's find our tangential acceleration first. So we'll do that here. So our tangential acceleration is, well, we already figured this out. It's alpha times r. What was alpha? An honest question, I don't remember what it was. 0.07 radians per second squared times our radius is 3.5 meters, right? So that's going to give you 24 and a half. So 0.245. Is that right? I did that in my head. Meters per second squared. Is that right? Yeah. Now keep in mind this is rounded, so this is going to be off by a scotch because we didn't keep track of our sig digs. But cool. All right. So now we can also find our radial acceleration. So I know we know the angular velocity. Did we find the linear velocity? Yeah, we did. It was 1.1. So we can use either omega squared times r or v squared over r to find the radial acceleration. Anybody got a preference? Cool. Yeah, let's use the new one. That works. So our radial acceleration is omega squared times r. So our final angular velocity was 0.314 radians a second, right? We're going to square that and then multiply it by the radius. So let's see what that gives us. So 0.314 squared times 3.5. So that gives 0.345 meters per second squared. So before we finish the problem, let's, I guess, make sure that we understand how these two things are different. Okay? This guy, the tangential acceleration, is basically telling us how quickly the rider is gaining speed. Right? So every second, his speed is going to increase by 0.245 meters a second. That's what that number is telling us. Good? Now remember, even if you spin at a constant speed, you still have centripetal acceleration because your direction is changing, right? That's what this is measuring. Okay? It's telling you how quickly the direction is changing at that radius and at that velocity, at that instant. Yes?
Where do the units for radians go?
Again, anytime you use this R, well, not every time, but often when you use that the R, it's really meters per radian. And so, yeah, and it doesn't work out perfectly here. That was what I was saying. I said this yesterday. There's a little bit of occasionally some magic with the units. I mean, if we broke this down, I think that in order to make sense of this, we'd have to go back and re-derive this equation again using the geometry and algebra again. So it works, but I don't know that we need to spend a ton of time going into it. Is that cool? Okay. But this at least answers where one of them goes. All right. Are we good, you guys? I hope you don't mind that I'm being a little bit hand-wavy there. Okay, all right, so is everybody okay with what these two things mean? Okay, so my acceleration then is, well, I mean, I guess you could write it in unit vector notation, right? At that point up there, I could write this as, what, 2.45i minus 3.45j, right? And that would work at that point. Or you could just do the Pythagorean theorem, which would be, you know, take the square root of 0.245 squared plus 0.345. That's a weird coincidence. You know, and figure out what that gets you. Does that make sense, you guys? Okay, cool. All right, cool. I'm glad we did that because I think that I did not put that in the notes anywhere, and I know it comes up sometime this chapter. So. Oh, I don't know. I didn't see that. Oh, I gotcha. I understand. It would be the resultant, so it's going to kind of point this way, right? Because you've got a horizontal component and a vertical component. So here's your overall A. Solid? Everybody good? Okay. And this is not drawn to scale, obviously, because our radial should have been bigger. So. Cool. All right. I guess that's that. Worth pointing out that as the ride speeds up, this number here is going to stay constant for us, right? Because, you know, we assumed that it was gaining speed at a constant rate. But this will get bigger, right? Because as you spin faster, your direction is changing more quickly. So, all right. All right, so this is, sorry? You sure?
Yeah.
All right, so this one is basically just another exercise in making sure you understand how to use those constant acceleration equations. So let's do it. Let's write down what we know. Let's see, we got a motorcycle driving at 60 miles an hour, so our VI is 60 miles per hour. It's going to slow and stop, so our final velocity is going to be 0. That's all going to take 8 seconds. The tires have a radius of 0.35 meters. So A says, how many times will the tires rotate before the bike stops? So there's a number of ways of doing this. Thoughts? Sure, what do you got, Dave?
You might stop and how many circumstances that is.
Yeah, totally. That'll work 100%. Find the stopping distance using one of your linear acceleration equations, or constant linear acceleration equations, and then divide it by the circumference. Anybody think of a different way of doing it? Yeah, we got Alex. What were you thinking now?
I don't know. I felt like everything about acceleration and the velocity and acceleration.
I gotcha. Okay. Here's the other thing that jumped to my mind. How many times it rotates is change in theta, right? Okay. So the other option is find your linear displacement, use a jumper equation to find your angular displacement. That'll be in radians, and then divide by 2 pi to convert it to rotations. Okay. Honestly, I think David's way is easier, but the way that I said is at least using the equations that we've learned here. So either way works. Regardless, before I do anything, we got to get rid of miles per hour because our time is in seconds. So let's just convert everything to meters per second. This turns out to be 26.8 meters per second if you factor label that. So we can find our linear displacement by using 1/2 of VF plus VI times T. You will find you use these equations a lot this chapter, you guys. That average velocity times time thing comes up a lot. Okay, so we're going to get, what, 13.4 times 8, which gives us a number. Sorry. 13.4 times 8. So you got 107.2 meters. Cool. And then, yeah, just divide that by your circumference would work. So let's see, 107.2 meters times, here's how I'm going to write it. I know that one rotation is the same as 2 times pi times 0.35 meters, right? Because that's the circumference. Cool. And that's the same as using a jumper equation, dividing by radius, and then converting to radians by dividing by 2 pi. It's literally the same thing. Okay? So anyway, you end up getting 48.8 rotations. Cool. All right, so now let's find the angular acceleration. Thoughts? Two ways of doing this. Like I said yesterday, this chapter, more than any chapter we've done so far, there's going to be a ton of different ways to get from point A to point B. So,
On here, both squares, speed, and then the angular is the average.
yeah. Yeah, I think either way you do it, you've got to do 2 steps. You've got to jump from linear to angular and then find the acceleration. So the question is, do you find the linear acceleration and then jump to angular? Or do you find the angular velocity and then find the angular acceleration? You know what I mean? So let's do it the way Alex said. So let's see, we know our omega I, so that means, sorry, we know our VI. So our omega I is going to be VI over R, just by rearranging the jumper. So you get 26.8 meters a second divided by 0.35 meters. And you get, where's this other calculator? 6.8 divided by 0.35 gives you 76.6 radians per second. So now I can find my alpha by doing omega f minus omega I over t. So 76.6 minus 0? Oh, what am I doing? Sorry. 0 minus 76.6 radians per second, all in 8 seconds. And so you get negative 9.58 radians per second squared. Cool. Problems, you guys? So really, this section is just going to be about familiarizing yourself with that giant list of equations. You know what I mean? There's not a ton here that I can say conceptually that will, shed a ton of light on this. It's just, we're talking about a different type of motion now, angular instead of rotational. All right, cool. So we have 15 minutes here. Let's do this. All right, so a couple of quick comments about, so there are going to be some scenarios under which you'll have 2 things that will have the same angular velocity, and certain scenarios under which the 2 objects will have the same linear velocity. Okay, so on this wheel here, I've got different pieces of tape, right? So if I spin them, if I spin the wheel, what's the same there? For all 3 pieces of tape, they all have either the same linear or same angular velocity. Which one's the same? Angular velocity. Does everybody understand that? Because all 3 pieces of tape are going to take the same amount of time to turn through, for example, a 90-degree angle, right? Does that make sense? Which one's going to have the biggest linear velocity? The one farther out, right? Because it's going to go a bigger distance with every rotation, right? A bigger distance in the same amount of time, right? Cool? All right, now, in my honors class last week, I gave a problem about a bicycle called a penny farthing. You guys know what a penny farthing is? It's one of those bikes with a giant front wheel and a little back one. So can I, well, we've come this far, I'm going to finish it. All right, so here's the seat, here's the dude. It's called a penny farthing. Is that okay? Like, this is the seat, right? Okay, so remember, one of the things we talked about yesterday was this idea that every time this tire rolls around once, the bike is going to go a distance equal to its circumference, right? Okay? So in the time it takes for this wheel to spin one time, the bike will go this far. How many times is this wheel going to spin? Just once?
No.
No, this one has to spin a whole bunch of times to keep up, right? So this one's going to have a bigger angular velocity, right? Okay? Now, imagine that I painted the outside edge of this tire red and the outside edge of this tire red. Which point on the outside edges of the tire is going to be moving with a higher linear velocity?
Still be equal.
They're the same because they're on the same bike. So if the bike is going at 10 miles an hour, then this point is traveling with a tangential velocity of 10 miles an hour around the tire. Does that make sense? Cool? All right. At some point, you're going to see some stupid gear problems or some like things connected with belts. All right. There's a problem on one of the homework assignments in either chapter 10 or 11 that's got these wheels connected with belts. It looks something like this. So you've got a wheel connected with a belt, and then there's another wheel here that connects to another belt, or I don't know, it's something like this. All right. So, but honestly, it's not bad. It's almost more logic than it is physics. All right. So check it out. Let's suppose that we knew the radius of all three tires. Okay. So let's give them names. Let's call this R1, and we'll call this one R2, R3, and R4. Right. Okay. So assuming that the belts don't slip, what's going to happen? So this thing's going to be spinning with some angular velocity. Let's call it omega 1. Cool? Well, if the belt's not slipping, that means that I know the velocity of the green belt, right? What would it be? How would I find the... So there's one point on this belt that's painted blue. So how quick is that point going around and around? Yeah, the tangential velocity, right? So this thing here has a velocity of omega 1 times R1, right? So V equals omega 1 times R1, right? Oh, well, that means that a point on the outside edge of wheel number 2 has to have a linear velocity of this, right? Follow? Oh, and I know the radius. So now I can do, oh, well, omega 2, that must be whatever that velocity is divided by that radius. So now I know the angular velocity of this wheel. Does that make sense? What's the angular velocity of wheel number 3? The same, because it's connected to wheel number 2. Follow? Do you see what I'm doing? So all we're doing is we're just realizing that the green thing determines the velocity, right? The belt determines the velocity of a point at the outside edge of the wheel, and the wheel has some fixed angular velocity anywhere on it. Does that make sense, you guys? Okay, those gear problems where you've got gears with teeth, same exact idea. The outside edges travel with the same linear velocity. What's different is the angular velocities. Yeah.
This is like too complicated. How does what is like the relationship between angular velocity and velocity differentials, and gear differentials?
Yeah, that's there's a lot going on there. Because no, that's okay. That's okay. So let's talk about the penny farthing for a minute. This indirectly will answer your question. Why do you think they built this thing with the front tire so big?
I have no idea.
You have an idea?
Well, I mean, I just looked it up, so is it okay?
Yeah, sure.
Alright, so
And I've never looked it up. I'm just guessing. I think I know the reason.
one rotation of the pedal equals one rotation of the wheel back then, and so one rotation would equal a longer distance.
Exactly. Look, your feet do this. They go, right? And during that time, you travel however far that radius is, right? Exactly. So, and gears are sort of working on that idea. It's sort of the ratio between how much torque you're providing. That's determined by the front cog, and then the back cog is going to determine It's this. Here, where's my drawing? So let's see. The smaller this wheel is, the more times it's going to spin around per second. And so that'll make this go faster, right?
Yep.
But it takes more torque to drive it. So I don't know if that answers your question, but
I sort of